About solids, we've talked about liquids and solutions. You know what? I think I want to talk about gases now. So gases get their very own unit because they're completely different from the other states of matter. Solids, liquids, they're both fairly compact and dense. Gases, though, on the other hand, they are crazy. They're spread all over the place, bouncing off the walls, causing pressure, and as a result, we tend to focus on them a little bit different. So here's some properties of gases that you can take a look at, but just gases are all around us and they're kind of our unseen guest. As you're walking around, you're breathing them in, they're running into you, they're actually pushing down on you right now with 15 pounds of pressure. They cause water to boil or not boil, they cause our soda pop to be fizzy, they make balloons float and they keep us alive, so they're really important. So first property that is unique to gases is pressure. Pressure, we know the term. What it actually is force divided by area. And the force over area is important. If we think of a square area that's smaller and a square area that's larger, if you were to apply the same amount of force, we'll say 5 newtons, on each of these areas, this smaller area is going to feel more pressure than this area will, because in this case, the force is spread out over a much, much larger area. Think of someone who comes up behind you and pokes you in the back with a finger. They're poking you with a force over a very, very small area, just the tip of their finger, and that tends to hurt. As opposed to they come to you and just kind of pat you on the back, same amount of force, but it's a larger area because it's a full-blown hand. So the force is larger. The area is larger, and the force is still the same, and so we don't feel as much pressure that way. So gases create pressure by bouncing off the surfaces. We know about the kinetic theory, so the more energy, the more motion. Gases have the most motion they can get. At that point, they're flying, they're bouncing off of things, and when gas particles hit the side of a container, that causes pressure. And so since we have billions upon trillions upon Avogadro's numbers worth of gas particles in a container, they're constantly hitting on the sides. So a balloon with all those gas molecules constantly hitting against the sides, constant pressure is inside of there at a particular temperature. Gas pressure is not dependent upon gravity, so we actually feel gas exerted in all directions. So if you hold your hand out straight in front of you, you're feeling gas pressure on top of your hand and you're feeling it underneath your hand. And it's the same amount on both sides. And it's always 1 atmosphere. In terms that we can understand, it's 15 pounds per square inch. So that means every square inch of your body, if you measure off kind of an inch by inch area on the back of your hand, that feels the pressure of 15 pounds. Now, it's not really crushing your hands like a 15-pound weight would because you've got the same amount of pressure on the other side of your hand. So they kind of even each other out, but they're squishing it in between. And so we're constantly under pressure. And it doesn't crush us because the gases or the liquids inside of our body actually push back with the same amount of pressure. So if we imagine a metal can that's filled with gas, okay, it's just a metal can that's open, sitting there, there's gas pressure on the outside, 15 pounds per square inch, 1 atmosphere that's bouncing off of it, but it doesn't crush the can. Why doesn't it crush the can? Because there's gas on the inside of the can that is pushing back out, and so they balance each other out. These are going to hit and those are going to hit right back, so as a result, nothing changes. However, if we hook a vacuum pump up to a bottle and we pull the air out from the inside, as a result, there wouldn't be anything to cause pressure inside of the can, and so the pressure inside is now going to be less than the pressure outside. If the pressure inside is less than the pressure outside, that means that 15 pounds per square inch is going to be able to crush that can. So gas pressure is actually one of the oldest atmospheric conditions that we've been able to track. And we've tracked them throughout history with what's called a barometer. And so this is actually what they used to use to predict weather ahead of time because pressure outside, so the air pressure around us, varies with weather patterns. And so we can see, hey, is it going to be rainy? Is it going to be sunny? Just by looking at the air pressure outside. And the way this is done is originally with a dish of mercury. Mercury is a liquid metal, and so they would fill a dish with mercury, put a little tube over the top that has no air on the inside. What's going to happen then is atmospheric pressure is obviously pushing down on that metal liquid, and when it pushes down, it can push that liquid up here. Because the pressure down, there's no pressure up here to hold that liquid except for gravity, and so it's able to move it up or down. If you increase the pressure out here, it's going to lift that even higher. And so that's what they would call millimeters of mercury. So they would measure the distance up that the mercury would go. The higher it went, the higher the pressure. And atmospheric pressure turns out to be about 760 millimeters of mercury. A new term for millimeters of mercury is torr. They really mean the exact same thing, though. It's just that no one uses mercury for a barometer anymore. Now you see over here, if we have an open-ended tube, that mercury isn't going to go up the open-ended tube because since it's open, air pressure from the outside could push it down right there too. But over here, since there's no air pressure inside there, the air pressure outside can push it up. This is the same way a straw inside of our drink works. When you put your mouth over the top of a drink, you pull the air molecules out, thus creating a low pressure zone, and so atmospheric pressure is able to push the drink up the straw and into your mouth. I'd be remiss if I didn't talk a little bit about temperature and gases. So temperature, of course, is a measure of average kinetic energy of atoms or molecules in a system. The Kelvin temperature scale is proportional to this, and so when Ke doubles, the Kelvin temperature doubles. If Ke were to cut in half, then the Kelvin temperature would cut in half. The mo energy, the mo heat, the mo motion. So there's three ways that gas molecules can move as they're traveling through space. They can move in straight lines, which is called translational energy. There's rotational energy, which is just them spinning as they move through space. So you think of throwing a baseball, that baseball is spinning as it's moving through. And then vibrational energy. So as they're moving, there is going to be a little bit of vibration in there too. Most of the energy, most of the kinetic energy of a gas molecule is going to be translational energy. It's going to be the energy to move it from one side of a container to another. So one of the assumptions of gases that has to be considered when we're considering an ideal gas is the fact that all collisions are completely elastic. What that means is when a gas molecule bounces off the side of a container, the kinetic energy before and after stays the same. Now in the big world, we know this isn't true. If you were to take a ball and bounce it off the wall and then catch it, you would notice that when it comes back to your hands, it's not moving at the same speed that you threw it with. It loses some of its energy when it bounces off the wall and comes back, just due to friction, actually with air molecules and other things. But in the gas world, we consider a complete bounce. So imagine throwing something and having it hit back in your hands with the exact same speed that you threw it with. So at a certain temperature in the room, not all of the gas molecules are going to be moving with the same amount of kinetic energy. Some will be moving faster, some will be moving slower, but most of them will have a certain temperature or a certain speed right there, kinetic energy. And so that average would be the center of that bell curve, would be the temperature. So 250 Kelvin would be right there. So really the temperature in a room is an average of the motion of the particles. And since pressure is also dealing with the motion of the particles, pressure is also based upon the average kinetic energy of the gas particles in a room.